Hello everyone, thanks for joining us. Today we're going to be looking at Concorde and I'm going to be arguing that it was in many ways Europe's moonshot. So join me over the next 35 to 45 minutes as we look at some aspects of Concorde, its design, history and so on. What am I going to cover during this lecture? So we're going to cover an introduction to the series. This is actually the third sort of technical presentation that I've made over the last few months. These are really recordings of lectures that I've given online to various people for various reasons. And we're going to look at an overview of Concorde, some of the key facts and figures that are involved in it. We're going to look at the design features of Concorde, some of the things that allowed it to do what it managed to do. And we're going to put it in some limited historical and technical context. I'd obviously have to put a caveat on that this is a relatively short talk and I can't go into any meaningful historical detail in such a short period of time. And I'll be looking at whether, in my opinion, it constitutes a success or failure and debating some of the points that are around that. So with that in mind, let's get started. So first of all, why am I doing this? Yeah, it's a good question. It's fair to say that since I was a kid, I've been pretty fascinated with technology, and much of the machinery that did fascinate me as a kid was British or European. Now, that's not necessarily because it was the best stuff there was, it was merely because that was where I grew up. You know, if I'd grown up in America, I might be fascinated by big muscle cars, and if I'd grown up in Germany, I'd probably be fascinated by whatever they do there. But I didn't. And so some of the machines that fascinated me were obviously these JCB excavator type diggers. In fact, the first word I ever said was digger, and I got into quite a lot of trouble when I was about 7 with my significantly more artistic mother, who had dragged us up some dismal mountainside in Austria with some sketch pads under the assumption, I didn't realize it at the time, that we would draw nature in all its glory. Well, of course I didn't. I drew a JCB. You can imagine the consequences. The British Intercity 125, probably one of my favourite trains, still reliably operating after more than 40 years of service. I sat in a cab of one of these when I was 5 with my mother's cousin in Bristol Temple Meads, and it's sort of stayed with me ever since, and I still think they're fascinating, beautiful pieces of equipment. And then the space shuttle, of course, which is something I would love to do a talk on and may well do at some point. Again, one of those pieces of equipment that has, in my opinion, a relatively unfair, bad press, because regardless of its economic performance, it was nonetheless an enormous engineering achievement. And that is really how I feel about Concorde as well, which is a very similar sort of thing, that maybe it did cost a bit of money to build and maybe it wasn't particularly useful to the majority of people on Earth. But as we'll look at during this presentation, it did influence the world we live in to a degree that I think is much greater than most people want to acknowledge. And it did change the world, generally for the better, and I'd like to talk about that during the rest of this lecture. Okay, let's look at some key facts and figures of Concorde, a plane that I would argue is the most recognisable in the world. Even people who don't know anything about aircraft probably recognise the Concorde. There's a lot of reasons for that, and some of these numbers might help illustrate why. So first off, it had its first flight in 1969, March the 2nd. That was before Neil Armstrong landed on the moon, although it was after the first Apollo mission circumnavigating the moon took place. It was a different era, something people of my generation can't really imagine. It entered service about 7 years later on the 21st of January 1976. Now that's a relatively big development time, even by today's standards, between first flight and service entry, and that reflects the complexity of the aircraft. There were significant differences between the first 2 prototypes and the production aircraft, and those kinks did take a while to iron out. Its last flight was October the 24th, 2003. And that gave a service length of 27 years, 9 months and 3 days, which really isn't a bad effort for a commercial airliner. Obviously, there are occasional other airliners. I'm thinking there's still DC-3s in service, which have been in service for 70, 80 years in some instances. However, I would say for an unmodified or significantly unmodified aircraft to remain in service for that length of time, never mind the fact that when it went out of service it had no direct replacement and still doesn't, is a testament to the quality of the aircraft and the fact that it did what it did so well. 27 years, 9 months and 3 days is not a bad innings for any piece of machinery. Most of us don't have cars, for example, that have been in service for that length of time. It had a relatively high takeoff speed of about 400 kilometers an hour. Now, typical jets are about 220 to 280 kilometers per hour. So that high takeoff speed necessitated significant improvements in brakes and tires. So a lot of people might think that the Concorde had very good brakes and very advanced tires because of its high landing speed. Actual fact, its landing speed at 274 kilometers per hour wasn't anything remarkable. The reason that it needed those good brakes and good tires was because in a rejected takeoff scenario, it needed to be able to stop in the length of runway available to it from a much higher speed than a typical aircraft would have to do under those circumstances. Its range was 7,200 kilometers at supersonic cruising speed. Now, that is a healthy range, depending on which way you look at it. It's just enough to make the Atlantic crossing. However, if you compare it to a modern long-range airliner like a 777 or a 787 or an A350, that is not a great range. Those aircraft typically have 2 or 3 times the range. So it was a medium-range airliner, you could say, by today's standards. Nonetheless, it is the only supersonic aircraft that had anything like that range that's ever been built, never mind entered service. Its passenger capacity was similar to something like a small 737, 90 to 120 people. That's not a great deal of people. It depended on the configuration, of course, because Air France and British Airways, the two operators, had slightly different configurations. And it carried about 96 tons of fuel. In actual fact, it would leave the gate with something between 98 and 100 tons of fuel because it would burn about 2 tons on the way to the runway. Now, that burning of 2 tons on the way to the runway was unavoidable, but there were also reasons that it couldn't take off with 100 tons of fuel that were to do with fuel tank design and airlocks therein. It had a takeoff weight of about 187 tons. Now, that's actually quite big. It's similar to something like a Boeing 767 in the medium versions of that aircraft. So Concorde wasn't a small aircraft. It was a relatively big aircraft. It carried a relatively large amount of fuel, similar to a modern long-range aircraft. It had a medium range and a relatively low passenger capacity, and it traded that medium range and low passenger capacity against a very high cruise speed. Essentially, these were trade-offs that just had to be made in order to achieve that high cruise speed. Right, more facts and figures. The engines on Concorde, it had 4 Rolls-Royce Olympus 593 turbojets. Now, as you'll know from my previous talk on aircraft engines, turbojets are seldom used these days because they have lower efficiency at the cruising speeds of typical aircraft. However, they are efficient engines if you want to go supersonic, and that was exactly why turbojets were chosen for Concorde. In fact, as far as I know, those Rolls-Royce 593 Olympus engines are still the most efficient engines that have ever been built at Mach 2 cruising speeds. They weren't particularly powerful engines by today's standards. Each one was about 32,000 pounds of thrust dry. That means without afterburner. Concorde obviously had 4 afterburning engines. Those afterburners dump fuel into the tailpipe, which increases your thrust slightly at the cost of significantly increased fuel consumption. And the afterburners would bump the engine thrust up to about 38,000 pounds. Now, for comparison, a modern big turbofan like a Rolls-Royce Trent XWB has 97,000 pounds of thrust. So more than 3 times as much as an Olympus on dry mode. However, of course, you're not comparing apples with oranges. The XWB engine is a turbofan and obviously could not travel at Mach 2 or anything close to it. Its typical fuel consumption was around 25 tonnes an hour, which isn't too bad really. When you mut it by the minute, that's 415 litres per minute. One cool thing about Concorde was that due to the kinetic heating caused by friction between the air and the aircraft skin at Mach 2, that generates a lot of heat. That heat has to go somewhere, so the designers incorporated heat exchangers where the fuel that was going into the engine at that high fuel rate of about 100 litres per minute per engine would take the heat from the aircraft cabin, which was created through skin friction, and dump it into the fuel, thereby heating the fuel slightly before it went into the engines. And that was a relatively efficient way of cooling the aircraft. Without that, you could run the risk of boiling the inhabitants, which would generally not meet with a great deal of happiness. As I said, she did have afterburners, but she only needed them for takeoff and the transonic period. So the transonic period is between about Mach 0.95 and Mach 1.05. That is the period when the drag on the aircraft is the highest. So you needed them for takeoff due to the relatively low efficiency of the delta wing at low speeds and high angles of attack. Other than that, she didn't need afterburners, and she could accelerate to Mach 2 from about Mach 1.05 without afterburners at all. And again, she is the only aircraft ever built that I know of that had that ability to do it. These days, that ability is known as supercruise. Cruising in supersonic speed without afterburners is known as supercruise today, but in those days it wasn't known by that terminology. There's a couple of fighter aircraft that can supercruise now, but they can't supercruise at Mach 2. She was made out of aluminium, which I'll go to in a bit more detail later, but it was a relatively pragmatic choice for the requirements that they had. And the skin temperature, as I said, would be about 127 degrees at the nose, dropping off to around 90 degrees around the tail area and wings. And that high temperature was caused by the high speed of the aircraft moving through the air, encountering a lot of friction. Obviously, that heat would heat up the entire aircraft and it would expand in flight. In addition, of course, if it wasn't for the fuel system that I've already mentioned, taking that heat away and dumping it in the engines, then the cabin would become lethally hot. Right, so Concorde was one of only 3 aircraft capable of extended duration supersonic flight. Now, what I mean by that is supersonic flight beyond Mach 1 for periods exceeding about 30 minutes. Obviously, many military aircraft have been able to exceed the speed of sound since the 1950s. However, in a majority of cases, they've had a very limited supersonic endurance because they're either not big enough to carry sufficient fuel to travel for an extended period at supersonic speeds, or due to the multi-role nature of the aircraft design, they've been optimized towards lower speed operations. Now, it may be that some bombers are capable of extended duration supersonic flight, but it's very unclear to me that that's the case. And even the bombers that are capable of supersonic flight appear to be operated mainly in the subsonic regime, only entering a supersonic dash for the final phase of their mission. The other 2 aircraft that were capable and did travel for extended duration beyond the speed of sound were the Soviet equivalent of Concorde, which was the Tupolev Tu-144, and the American spy plane, the Lockheed SR-71. The Tu-144 is an interesting aircraft. A lot of people reject it outright as a sort of slightly inferior Concorde copy, which I don't think is entirely fair. However, it was unsuccessful for a number of reasons, and I'd happily talk about that another time. The SR-71 is a different kettle of fish altogether. It was a higher performance aircraft than Concorde. It could and did cruise at speeds in excess of Mach 3. However, it was a very high maintenance, specialized piece of equipment that you couldn't really compare to Concorde, in the sense that Concorde was a relatively standard commercial airliner that operated commercially from relatively standard airports, although it did need some bespoke ground equipment. Notably, it didn't have an APU and the engines couldn't start without a ground card. However, it didn't take 24 hours to prep Concorde for a mission, and of course it had a much bigger payload. It was the only successful supersonic transport. I've put the word successful in quotes because obviously many people would argue that it wasn't that successful. However, in this instance, I mean being in service for 27 years, 9 months and 3 days. The Tu-144 only entered service and stayed there for a few months, and even then it was relegated to carrying mail. It was the only aircraft that was capable of Mach 2 flight without afterburner. Even the supercruising fighter aircraft of today cannot travel at anything like Mach 2 without afterburner. And more people have flown supersonically on Concorde than all other aircraft in the world combined. In other words, if you're a civilian, you are more likely to have traveled at a supersonic speed than anyone else. So well done. This is a fact or a suggestion that was made to me that I've been unable to verify, but wouldn't be surprised if it was true, that it's suspected that Concorde spent more hours flying supersonically than all other aircraft combined. Now, that may have been true up until the point that Concorde left service in 2003. I suspect it definitely isn't true now, what with the explosion in manufacturing of fighter aircraft and the remilitarization of the world. However, it may be true. I can't find a source for it. I put it there more as something to think about than a statement of fact. So if we now look at some of the technical features that made Concorde able to do the things that Concorde could do, arguably one of the key features of Concorde, and probably the most recognizable thing, is the wing. Now, Concorde had an ogival delta wing. So a plain delta wing that you might see on something like a Dassault Mirage, for example, is literally just a triangle. It would look something like this. And delta wings have exceptional high-speed performance for a number of reasons, which is why they tend to be used on very high-performance aircraft. However, the problem with the delta wing is that in order to achieve low-speed handling characteristics, the delta wing needs to operate at a very high angle of attack. And what an angle of attack is, it means that the angle of the aircraft wing relative to the direction it's traveling in. So, for example, if it is at an up angle but traveling horizontally, that has a high angle of attack. And it needs to do that at low speeds in order to generate sufficient lift. Now, that has a concurrent knock-on effect on both handling and efficiency. With the handling, low-speed handling on a plain delta wing is really not very good at all, and obviously the efficiency is also low. Now, Concorde obviously is optimized for high-speed cruise, so the delta wing was the obvious choice. However, research projects in the UK in the 1950s led to the development of the ogival delta wing. So notice here it's essentially a smooth, rounded delta wing shape, and it also has a lot of camber at the edges. Now, what that does is it promotes an effect called vortex lift. Vortices are a thing that happen on any wing. It's basically the air rolling off the wing in a spiral pattern. Now, what was noticed during the development of Concorde's wings was that these vortexes were increasing the speed of the airflow over the top of the wing. And that in turn was increasing the lift due to Bernoulli's principle. But these vortexes are at their strongest when the aircraft is at a high angle of attack. So the wing, which would happen when the aircraft is at a relatively low speed, and that meant that the wing was tweaked with these additional aerodynamic features in order to promote the generation of these vortices at low speed and high angle of attack. And that is how the Concorde was able to land at a speed that was comparable to other aircraft, albeit in a manner that required a lot more engine power. If that had not been the case, additional control surfaces may have been required. For example, canards on the front of the aircraft or a tailplane on the back would have been necessary, and that obviously would have added extra drag and weight, and or a much higher landing speed would have been required. And both of those solutions were adopted by the Soviets with the Tu-144. So Concorde did have a very sophisticated and very advanced wing that allowed it to perform very well at high speeds, but also adequately at low speeds and high angles of attack. The other famous thing about Concorde is the drooping nose, which we can see here on this GIF that I have shamelessly stolen. The reason for the droop nose is twofold. One, in order to get a good supersonic performance, you need a very aerodynamic nose, and that requires a long pencil-shaped nose. But the second thing is that, as we saw with the aircraft wing, the high angle of attack needed at landing means that the aircraft has to point up quite a lot on the landing run, and that means that if the nose was high, the pilots wouldn't be able to see the ground. So the nose folds out of the way for landing in order to give the pilot a better view of the runway at high angles of attack. We can see that in a slightly better mode here on this slide. Notice the very high angle of attack that the aircraft has relative to the ground. That's this angle here, which is significantly higher than normal jet aircraft because of the need to get the vortex generation over the wings at the landing and takeoff configurations. The landing gear on Concorde, therefore, had to be much higher than a typical aircraft in order to stop the back of the aircraft bumping onto the ground. Unusually, Concorde also had a bumper at the back, which was there to prevent or reduce the damage caused by a slightly over-enthusiastic landing or takeoff. Now, as well as being quite long and spindly, Concorde's landing gear was very, very sophisticated. It had carbon-carbon brakes, which was developed specially for this aircraft, which are routine today. And the tires were developed specially by Michelin to allow very high speeds. Obviously, as you may know, there were issues with the tires, but nonetheless, they were very good considering the performance that was required from them. Among the many things that the Soviets could not duplicate with their Tu-144 were the brakes and the tires of Concorde. And in their case, it was an even more severe issue because the landing speed was so much higher. If you look at pictures of the Tu-144, they had something like 16 tires per bogie, as opposed to the 4 tires per bogie on the Concorde. And that was because their tires just weren't up to it. Obviously, that had a knock-on effect on high weight. You know, that if you're carrying tires around, you can't carry fuel and people, and therefore it was another reason the aircraft was less successful. Right, so Concorde had reinforced carbon-carbon brakes. Reinforced carbon-carbon is a composite material which is essentially graphite mixed with carbon fiber. Now, this can take a very high temperature. It's maybe most famous as the ablative material on the space shuttle. This was the first ever use of reinforced carbon-carbon brakes on anything, and they were developed specially for Concorde. The prototypes actually used steel brakes. Now, carbon-carbon can take very high temperatures, and that's important because when you're trying to dump a lot of kinetic energy and turn it into heat, which is what a brake does, then the brake's going to get very hot. You have two choices at this point. You either have a brake material that can withstand extremely high temperatures, or you have to have a physically bigger, heavier brake so that the same amount of kinetic energy is distributed over a much wider mass, and thereby giving you a lower temperature. Now, obviously on a supersonic airliner, low mass is better, and that's why reinforced carbon-carbon brakes were developed. They were multi-disc brakes, which are similar to a multi-disc clutch. If you look at this picture here, you can see that every other disc is keyed onto the rotor, and every other disc is keyed onto the stator, the axle, which means that the discs move relative to each other. When you push one end of the disc, the whole stack compresses, and that activates your brakes. They had anti-lock features. These had been used on aircraft before, but nonetheless they were still a fairly advanced piece of kit at the time and were vital in terms of bringing aircraft to a safe stop, particularly in a rejected takeoff scenario. And they had electric hub-mounted cooling fans to try and dissipate some heat. You can see here these holes in the hub to allow the fans to breathe. The engines, as I said, she had 4 Rolls-Royce Olympus 593 engines in 2 pairs, 1 on each wing. Now, these engines were turbojet engines, and actual fact, when we look at the engine groupings on Concorde, most of what we can see is the intake system and the afterburner system. The Olympus engines themselves are relatively small. They were both afterburning and thrust reversing, which again was the only instance that I know of on an aircraft where they had both. And they're still, as I said earlier, the most efficient engines for Mach 2 cruising. It's not to say we couldn't design a much more efficient engine now, it's just nobody's asked us to. These engines were a very successful and reliable engine. They were widely used for other purposes, as well as Concorde, power stations notably, and also ships. So this is one of my old ships, HMS Nottingham. She had 2 Rolls-Royce Olympus engines, as well as 2 Rolls-Royce Tyne engines in there. And many times I've started and stopped them, and I found them to be a really solidly built, well-designed, reliable engine. These engines, although they are Rolls-Royce engines, were actually originally designed by Bristol. Bristol used to be a competitor to Rolls-Royce back in the day, and the reason that you can tell whether it was a Bristol design or a Rolls-Royce design is because Bristol engines were usually named after Greek gods, so Proteus, Olympus, and so on. Rolls-Royce engines were usually named after rivers, so Tyne, Trent, and so on. Rolls-Royce eventually assimilated Bristol. These were good 2-spool, fairly simple turbojet engines that didn't really give Concorde any trouble over its life. More complicated really than the engines is the intake control system. So if you want to travel at a supersonic speed, particularly speeds of Mach 2, you need to have a fairly complex air intake control system. This is not something you need to worry about at subsonic speed. The reason for this is that if you have air entering the engine at a supersonic speed, it's simply going to destroy your engine. So you need to have an intake system that allows the engine to breathe at subsonic speeds, but then slows down the air sufficiently and spills off excess air at supersonic speeds so that it doesn't knacker the front of your engine. Now, on supersonic aircraft that are designed for high speeds, the intake system has to be relatively complicated. If it's just going about Mach 1.2, Mach 1.3, you might get away with it. And there are new developments such as diverterless supersonic inlets, which can operate, I believe, up to about Mach 1.6. If you want to go Mach 1. If you want to go Mach 2, though, you do need a controllable intake system. Concorde used a system of ramps and spill valves to control the air intake. Here we can see the front ramp here and the rear ramp here, and they're in the down position on this computer graphic. Here you can see them in the up position. So at supersonic cruise, the ramps would be in this position here on the right, where they're down. That both positions the shockwave, slows the air down to subsonic speed, and bleeds off additional air around the engine that is not needed for combustion purposes. At takeoff, the ramps are in the up position to allow the maximum amount of air to enter the intake. It had a noise abatement climb mode, which essentially tried to mask the engine noise a little bit by routing additional air around the engine. I'm not sure how effective that was, but it was there. And obviously it also had a reverse thrust mode where all the spill valves were open and the reverse thrusters directed the thrust at an angle in order to bring the aircraft to a halt. Now, this intake system was computer controlled, as were the engines. It had to be, because this needs to be positioned very accurately and very reliably and very quickly. Not only that, it had to be designed specially to react in the event of engine failure. One of Concorde's biggest risks was considered to be a dual engine failure on one side. These podded engines were quite a long way off the center line of the aircraft. So in the event that one engine exploded and took the other with it at, say, Mach 2 flight, it was thought that the aircraft would instantly roll into an uncontrollable situation. So computer control systems were designed especially to react to that exact scenario. Another problem the Soviets had with the Tu-144 was that they couldn't place the engines in that outboard position, which for various reasons was more aerodynamically efficient, because they couldn't develop suitable electronics to react quickly in an engine out scenario. As I said, the variable geometry intakes ensure air enters the engines at under. Now, let's look at the flight control system for Concorde. It was the first use on a production aircraft of fly-by-wire systems. Now, Concorde had an analog fly-by-wire system, and it's important to distinguish that from the more modern fly-by-wire systems that were first deployed on passenger aircraft with the A320 in 1988, which was a digital fly-by-wire system. A fly-by-wire system is simply an electrical connection between the control column, or the pilot's control system here, and the actual control surface. So the control surface are elevators, elevons, horizontal stabilizers, rudders, spoilers, and so on. On Concorde, having a delta wing, she had various elevators at the back which operated either independently or combined to give pitch and roll control, and she had twin rudders on a single fin. Now, what they did was, on the control column here at the front, there were position sensors. Those position sensors fed their position into some analog signal processors, which sent a signal to an actuator, which was still hydraulic, on the actual control surface itself. Now, what that means is that you don't have a physical connection, i.e. wires or rods, between the control column and the control surface. It gives you significant advantages when it comes to integrating autopilots, for example, because the autopilot can simply give an alternative electrical signal to the actuator. And that was the main reason that Concorde went for this fly-by-wire system. She also had a quite interesting strain gauge system mounted on the control column, which was there in case the control column itself became locked for some reason. It was still possible to fly the aircraft with a locked control system because there were strain gauges on the control system. So the act of bending the control column, even if it wouldn't move, would impart a force into the strain gauge sensors, which would then actuate the control surfaces. That was the first reversionary mode. She also had a second reversionary mode, which was a conventional mechanical link between the control column and the actuator. Now, you might say, if there's a mechanical link, why did they bother going into the electrical system in the first place? It wasn't a particularly strong or robust mechanical link. It wasn't designed for continuous use, so it still saved weight by having a relatively lightweight mechanical link. And also, as I say, one of the big advantages of the fly-by-wire system was easy integration of the autopilot control system. So even with a mechanical link, it's still an advantage to have a fly-by-wire system. Now, the difference, as I said, between an analog fly-by-wire system and a digital fly-by-wire system is that the analog signal processors cannot be reprogrammed or modified easily. On a digital fly-by-wire system, such as used on the A320 from 1988, the actual flight characteristics can be tweaked by adjusting the flight control computer. The computer takes the sensor information from the control column, processes it in accordance with algorithms that we set, and can adjust, and then gives that to the control system. So it gives you significantly more flexibility, particularly through the development of the aircraft. Concorde had an advanced, fully integrated autopilot that was capable of operating the aircraft without interference from takeoff through to supersonic cruise and all the way down to landing and rollout. And that was an extremely advanced feature for the time. It also controlled the engines, afterburners, and so on, which again was a very advanced feature at the time. With these fly-by-wire systems, it would be possible to have a fly-by-wire system where you have no control system feedback onto the control column. By that I mean it would feel a bit like moving anything that's not physically connected to something else. Without some pushback from the control surfaces, it might be very easy to overcompensate and overcorrect. So in order to avoid that possibility, the designers incorporated artificial feel into the control column. This was a series of actuated jack springs which provided resistance in the direction that the control column was moved. And that resistance was proportional to how much the control column was moved and how fast the aircraft was flying, which would basically mimic what you would feel if you were mechanically connected to the control systems as you would be on another aircraft. So yeah, again, flight control systems on Concorde had to be specially developed for the job, were world-beating, state-of-the-art systems that are still impressive today. Let's look at the structure of Concorde. Now, in many ways, Concorde had a relatively conservative structure. As I said before, she was made of aluminium. Now, there are many reasons for that, but there's also many reasons why you wouldn't make a supersonic aircraft out of aluminium. Aluminium is cheap, it's relatively easy to manufacture, it's lightweight, and it's well understood. At the time Concorde was built, aluminium aircraft had been under construction for some 40 years. There was a wealth of experience in how to do it, and there was nothing particularly remarkable about the way that the structure of Concorde was built. The designers, I think, took a very pragmatic, conservative view on this. So it's constructed from ribs around the fuselage and stringers which go lengthwise. The wing, typically wings have a spar or 2 or 3 central spars, and then the rest of the wing is hung off it. It's slightly different on Concorde only because it had a delta wing, which essentially has multiple spars effectively, and then this crisscross lattice support system on which the skin is hung. Now, that's fine, it works really well. The reason I say it was a relatively good decision was because it was a well understood technology, but it still permitted speeds of Mach 2. Why is the speed related to the construction material? Well, it's quite straightforward really. As we can see from this drawing up here, the temperature on Concorde rises as the speed increases. Right here on the tip of the nose, the temperature would be about 127 degrees centigrade. Even at the coolest parts around here on the tail, it's probably still around 90. We've already mentioned that that gives you a big headache in terms of removing the heat build-up in the cabin, which was solved by the fuel system. However, what I didn't mention is that it gives you a headache in terms of structural strength. Aluminium is a strong metal. It does, however, have a relatively low melting temperature. Now, don't misunderstand me, aluminium is not going to melt at 127 degrees. However, what it will start to do around 130 to 150 degrees, depending on the grade of aluminium, is soften. As it softens, it obviously loses some of its structural strength, and your aircraft will warp and fall apart in mid-flight. It won't happen instantly, but it certainly will happen if you cruise extended duration at very high speeds. Now, that fact about aluminium effectively limited Concorde's speed to around Mach 2.02. Obviously, it could go slightly faster for dash speeds or, demonstration purposes, but the cruising speed was effectively set by the construction material. The SR-71 Blackbird, the American spy plane, could travel at Mach 3 because it was made out of titanium. Now, titanium is another lightweight metal, although it's not necessarily as light as aluminium in some configurations, but it does have the advantage of being much better at high temperature. It's also significantly more expensive and harder to work, so you might get away with titanium for a military aircraft like the SR-71. However, with Concorde, that would be dragged around taxiways, it would be clipped into tractors and terminals. It needed to be something that could be repaired using equipment that was available at a typical airport and, skills that are available in a typical country. And titanium wouldn't really have cut the mustard for that. Not to mention the fact that titanium at the time was extremely expensive and difficult to come by. Quite famously, the SR-71 was built from titanium that was secretly imported from Russia. The other alternative material, which again the Americans attempted to use on their own supersonic transport project, was stainless steel. Stainless steel will easily tolerate these high temperatures, but it is much heavier than aluminium, and that gives you a headache in terms of payload, range, capacity, and so forth. As you may or may not know, the American SST came to nothing because, in my opinion, the choice of a Mach 3 cruise speed was just too ambitious for the economic situation at the time, never mind the technical situation. So yeah, Concorde had a relatively conventional structure, and I think that was a very wise choice from the designers. Okay, let's look at the historical context as best we can in a few minutes. Obviously, I would put a caveat on this that I am not necessarily an expert on these matters, and I am obviously going to have to simplify it quite a bit to fit the time. However, please feel free to join the discussion in the comments below, and I'll happily engage you there. The Wright brothers' first flight was in 1903. By the time World War II came around in 1939 to 1945, jet aircraft were developed, which travelled around 500 miles an hour, which is about Mach 0.8, depending on altitude and conditions and so on. There were some aircraft in World War II that were clocked at speeds in excess of Mach 0.9, but they had significant issues with control system failure or control system reversal or breaking up completely because of a phenomenon called compressibility, which occurs when you travel close to the speed of sound. Many responsible people thought that the sound barrier would not be broken by a manned aircraft because of how many people had died trying. However, in 1947, the incredible Chuck Yeager, who I could talk about for hours, did break the sound barrier in an experimental aircraft, rocket-powered, called the Bell X-1. That was a big achievement. The Bell X-1 was the result of a significant amount of research. It was a very strong aircraft. It was modelled after a bullet, and it had extremely thin, very strong wings. It couldn't take off under its own power. It was carried aloft by a B-29 bomber and then dropped in midair, whereupon the 4 rocket motors were ignited. And yeah, he broke the sound barrier, which was an incredible achievement. And the main thing about Chuck Yeager breaking the sound barrier was that it permitted research to be conducted at the supersonic flight speeds, and that allowed the development of much more sophisticated aircraft. So very, very soon after Chuck Yeager broke the sound barrier, it was possible to build supersonic aircraft that were capable of taking off, landing, and operating at supersonic speed without being dropped from a bomber and without using short duration rocket engines. That led in the 1950s to Mach 2 fighter aircraft. Now you might think, oh, Mach 2 fighter aircraft, well, that's pretty impressive. Concorde was a Mach 2 aircraft. These aircraft were very impressive. The F-104 from Lockheed, the Dassault Mirage 3 from France, the English Electric Lightning, the Soviet MiG-21. These are all aircraft that could and did operate at Mach 2. But they could only do it for a relatively short period of time. The Lightning is perhaps the most famous example of something that really didn't have much in the way of legs, but it did have an incredible climb performance and incredible acceleration, which befitted its role as an interceptor. These aircraft proved that Mach 2 flight was possible. However, it wasn't possible for very long. Entering into the 1960s came the space race. At this time, jet aircraft such as the Boeing 707 and the Douglas DC-8 became very popular. These aircraft weren't cheap to operate and the tickets on them weren't cheap, but they were very fast and very reliable, and passenger numbers began to increase significantly just because of the convenience, if not the affordability, of jet transport. That was a really significant factor. Now, those early jet aircraft traveled at very high speeds relative to today. So the 707 and the DC-8 did travel at around 600 miles an hour, which is verging on the sound barrier. Fuel wasn't such an issue then, and they didn't really mind. There was every reason to believe that passenger numbers would increase even further if speed could be boosted supersonically. This wasn't just a European thought. This was something the Americans were thinking. It was something the Soviets were thinking. It was a widespread belief at the time that speed sold. Fuel at the time was so cheap that it wasn't even really considered much of an operating cost to aircraft. Technology, maintenance, and crew were the main factors. Speed, of course, was very sexy. Faster was better. Everything at the time was being sped up. Fast cars, fast airplanes, fast women, you name it. It was all the rage. And at the time, there was a Cold War on, and for many of us, our memories of the Cold War are dim. Certainly mine. I only was born in the tail end of it. But we do have to understand that at that time, during the Cold War, technology was a goal in itself, because it was understood that technology would result in spin-offs which may have military applications, and the only thing that was important was some form of deterrence and protection from the other side, and that counted whether you were an American, whether you were a European, or whether you were in the Soviet Union. Technology and the development of it was given a much higher priority for its own sake than it is today in our sort of hyper-capitalist market-driven world. As I said, the Russians, Americans, and Europeans all believed, with good reason, that supersonic flight was the future and that people would want to travel supersonically. A common belief at the time was that future transport that was subsonic would only be for freight. And vast resources were spent by all three blocks on this. It's a point we'll go into a bit in a later, but the American SST project spent 3 or 4 times more money than Concorde. And unfortunately, all they achieved was a wooden mock-up. But the money was there and the money was spent. For various reasons, Europe was unwilling or unable to join the space race with the Americans and the Soviets. But at the time, again, for reasons that are relatively complex and historical, it arguably had the world's most advanced, if not successful, aviation industry. At the time, aircraft coming out of the UK and France were very, very good, well-engineered machines. They were just woefully uneconomic in comparison to the aircraft coming out of America. But they certainly had the technology to be able to do this, and certainly recognized that and decided to put it to use. So Concorde became not only a commercial proposition, but it also became a product of national pride. So Concorde was developed by Britain and France. It was essentially the unification of independent research projects that had taken place in both countries along very similar lines, and they basically pooled their resources in order to build it. So the engines obviously were British, a lot of the fuselage was French, and control systems came from both countries. So it was a very equal sharing of work that was used to develop this, and they had very good engineers on both sides. Its development costs were about 1.2 billion in 1970s money, and that translates to roughly 10 billion today. Now, that actually isn't a great deal to develop a supersonic aircraft. It's comparable to the cost that we used to develop the A380, which you could argue was also a failure in that it hasn't recouped its development costs. But it was around 3 times the cost of the development of the Boeing 747. However, there's a whole range of reasons for that. As we've seen, Concorde had extremely advanced technology, and all of that had to be developed, especially for Concorde. The 747, remarkable though it is, was built on the baseline of existing technology that Boeing knew and understood very well. The most remarkable aspects of the 747 were its size and its turbofan engines, but both of them had been already trialed on military aircraft, and so Boeing had access to that data, hence the relatively low development costs. Everything, in short, looked good for Concorde. At the time it was being developed, there were options from Pan Am, from El Al, from many other airlines. They expected to sell hundreds of these things, and they had every reason to believe that they would. There was a lot of hype, there was a lot of marketing, people wanted it, they wanted to travel supersonically, fuel was cheap, everything was going great. From our perspective today, it may seem obvious that Concorde would have been a failure. However, at the time, the perception was very different. So what happened? 1973 oil crisis predominantly. At that time in 1973, the Arab oil crisis struck and the price of fuel quadrupled, and it really hasn't recovered since. Fuel went from something that was so cheap it wasn't really considered to be that significant a factor in operating your aircraft to something that was suddenly extremely expensive. And as we've seen, Concorde, due to the fact that it was such a high-speed, high-performance aircraft, needed a lot of fuel. It probably burnt 2 or 3 times more fuel per passenger than a 747. Not only that, of course, it couldn't take as many people as a 747. So what happened was that the Boeing 747, which was an aircraft that was essentially developed on the cheap by Boeing as a backup aircraft, a freighter really, predominantly as a freighter, because they were spending all their resources and all their money and deploying all their best engineers on their, as it turned out, failed SST project. The Boeing 747 was unexpectedly the right aircraft at the right time. It was a very efficient aircraft. It could carry a lot of people and it didn't burn much fuel. Suddenly, the 747 was what people wanted. In addition, the moon landings occurred, which slightly restored American self-esteem in many ways. They felt like perhaps they didn't need to spend all this money and resources building a supersonic transport aircraft just to prove that they had massive big balls. That led to the cancellation or failure, really, of the US SST project, which I could talk about another time. It's, again, very easy to write it off. What they envisaged with that project was so much more advanced than Concorde that it's difficult to appreciate. It would have been a Mach 3 aircraft, and it would have been taking 200 to 300 passengers further, higher, faster. Those were incredibly ambitious goals, and as it turned out, they were really just too ambitious to be achieved, certainly with the money that was available to it. The US SST project cost significantly more than Concorde and achieved not much more than a wooden mock-up. At the same time, the Soviet Tu-144 failed essentially for many reasons. It was unreliable, it was noisy, it couldn't travel supersonically without afterburner, which meant that its range was restricted. Nobody really wanted it, and it was a bit crashy. So with the removal of the Tu-144 and the cancellation of the US SST project, then Concorde really was the only supersonic transport in town. That led the Americans to put some kind of political sanctions against it in terms of its noise. So it was banned from flying supersonically over land, which there was then followed by many other countries. And essentially that, combined with its high operating costs, meant that what had been considered to be the future suddenly became a niche product. I've already mentioned the success of the Boeing 747. That led to just 14 Concordes entering commercial service, 7 with Air France and 7 with British Aerospace. And famously, both of those companies paid £1 for each of those aircraft when they took them over. So was Concorde a success or failure? That really depends how you define those terms. Many people think of this photograph here. This is the tragic crash of an Air France Concorde in 2001. It killed 109 people. It's everybody on board. And there were a load of quite nasty reasons why that crash occurred, which weren't entirely unrelated to the fundamental design of the aircraft. They might think about the fact that just 14 Concordes entered service as opposed to hundreds and hundreds and hundreds of everybody else's aircraft. And they might think about the fact that only the very rich people could travel in Concorde. You or I probably couldn't. The ticket prices were over $5,000 one way. It wasn't something anybody could do. Although a lot of relatively normal people did as a special treat that they saved up for over the years. They might think about the fact that it was a very thirsty plane due to its very high performance, or that it was environmentally destructive because of the high fuel consumption and the possible degradation of the ozone layer. All of those things are true. However, I would argue it was a success overall. Concorde is the most famous aircraft in the world. People who don't know anything about aircraft know that this is the Concorde. They know what it's like. It was a source of enormous pride to Britain and France. It made them feel better at a time when their economies were struggling in the 1970s, when they'd lost their empires, when they'd basically gone from major world powers to third-rate tin pot countries. It was kind of a symbol that, yes, hang on, we still can do incredible things. It's an icon of European engineering. There's nothing really that's touch the world, I would argue, in the same way that Concorde has. Something that's so uniquely, inherently European, that it came from here, it was built here, and it was designed here, and it was unmatched by anything anybody else had. Obviously, that's all nationalistic pride reasons, and I don't think that's a particularly strong reason for success. More importantly, however, it was a technological marvel. Technologies developed in Concorde were deployed widely in other areas, and many of them are routinely used in aircraft today. However, Concorde had them 50 years ago. Reinforced carbon-carbon brakes, for example, anti-lock brakes, fly-by-wire control systems, fully automatic flight control systems from takeoff to landing and rollout, advanced composite materials, computer-controlled manufacturing methods. These are all things that were deployed on Concorde 50 years ago that we take for granted now, and these technologies simply wouldn't exist if Concorde hadn't been designed and built. It really was a technical marvel, and perhaps the biggest success of Concorde was that it indirectly led to the founding of Airbus, which is now the world's second biggest passenger aircraft corporation. The companies that were involved in building Concorde, which was predominantly British Aerospace and Sud Aviation in France, went through numerous mergers and reorganizations over the years, and eventually were merged into what became Airbus. And Airbus, as we know, is a highly successful corporation that in its own way has revolutionized air transport by acting as a viable competitor to American products and pushing technologies such as very high bypass engines, wide-body twin-engined aircraft, and digital fly-by-wire control systems, among others. Common family of cockpits, for example, allowing easy cross-training from aircraft to aircraft. So it could be argued that Concorde's biggest success was a demonstration that international collaboration was possible and was worthwhile, and therefore that led to Airbus. So overall, I would argue that because of its technical contributions and because of its business contributions in terms of its influence on Airbus, Concorde was a success, and it was worth the money that was invested in it. And in many ways, Concorde, being the technological marvel that it was, being in service for as long as it was, capturing the public imagination as much as it did, is in many ways the equivalent of the Apollo landings in terms of its achievements. With that, I'm going to close. Thank you as ever for watching. I'm sure you'll have a load of comments and queries and, of course, corrections that you can please put in the box below. And enjoy the rest of your day, and we'll catch you next time.